So I've summarized here on the whiteboard the result from our last formal example that started out with a single molecule bouncing back and forth in a box or container. And then I said, well, if there's n of those molecules doing that, the total pressure on the end caps would be equal to this expression here, which you asked, like, well, is there anything particularly interesting about that? Not yet. We're kind of on the way there, but there is this v sub x squared in here, and what I'd like to do is eventually be able to generalize to n molecules that are not all moving back and forth horizontally, but actually have random velocity vectors. And so this formal example we're going to look at here is going to give us some ideas for how to do that, because it says if v squared bar represents the average of the speed squared for all the molecules in a gas, and v sub x squared bar represents the average of the square of the x component of velocity, what is the relationship between these two quantities? And why this is interesting is if I look at the expression I had here, this has v sub x squared, but if I want to generalize my model and say, you know, this maybe just represents a component of a motion of a single molecule, how do I find an expression that represents sort of the average over all of them? I'm going to need this relationship, it turns out. So this is a formal example, so I'm going to pull up the answer and look at what it says. It says, since directions are completely random, the v squared bar, which something important about this is we're talking about take an individual velocity squared and then average. We're not taking the square of the average of the velocity. That would be potentially different. We're averaging after we've squared. And in that sense, when I say, well, if the velocity squared is equal to the sum of the squares of the components of that velocity vector, that makes sense because we know that that's true for vectors in general, that if you want the magnitude, normally you just sum the components squared and then square root, but if you don't square root, that gives you the magnitude squared. And then if you want to say now average all that, well, I'm just going to draw one big bar over it. That's what physicists like to do, to say average. But I'd like to argue, though, that that should be equal to the individual averages of the squares of these components. And that may be a little bit, the mathematics I would have to invoke, I think, to say why is that true is maybe a little bit beyond the course that we're doing here. But it might make sense, right? That if I'm going to say take the average of a sum of things, that that's equal to the sum of the averages. So that's what I'm saying here. But then if the directions are really completely random, shouldn't the average of the square of the x components be the same as the average of the square of the y components and the same as the average of the square of the z components? There's really no difference, you know, physically between going in the x, y, and z direction that would say that on average one of those should be larger. Well, you might say, well, what about gravity? Wouldn't that affect the y direction? But it turns out in the kinetic theory of gases, we're ignoring the effects of gravity, and these molecules are moving so fast that it turns out that that is actually quite valid. So if all three of these are the same, I could just kind of lump them all together as just being 3 times one of them. So I just say 3 times the average of the squares of the x component of velocity. And that implies that since v squared bar is equal to 3 times v squared sub x bar, that v squared sub x bar is equal to 1/3 of v squared bar, or in other words, v squared bar over 3. And so that's something that we're going to be able to use. So if this is true, that suggests that maybe this, so like here I said n molecules, but now I'm going to say n molecules and maybe I'll say just plus random motion, which by that I mean they're all traveling in random directions at random speeds. They're not just moving around like in a random path. They're all still kind of moving in straight lines until they collide with a wall. But you add those two things together, and maybe what should happen here is I would get pressure is equal to n times m, and then replace this v sub x squared with just v squared. and we'll put that bar over it. And maybe we'll see in a future example like what is another way to notate that, but we'll have to divide by 3 though, right? Because the expression we got at the end of this example says this thing is equal to that, divide by 3, and then I still need to divide. This is where things get a little confusing, by the way, because I've said divide by volume, so I have to be really careful here because this is v squared bar, which is the average of the velocity squared, and this is volume v. But I think we're going to expand on this a little bit in the next example.